we are going to start with the class. But first off, let me know whether we've all been able to install the software, the R, the Python, and whether we've been able to link the R to the Jupyter.
Done from this side.
Okay, thank you, sir. Right. So let's see if our software is working correctly. So I'm going to start. I'll start my Windows. That is, if you're on Windows, and then go to Anaconda 3, 64-bit. When you click on Anaconda 3, 64-bit, you will see a notebook. You will see Jupyter Notebook, which says Anaconda 3. Let's click on our Jupyter Notebook. When you click on it, a dark terminal will start. After a few moments, you'll find your Anaconda 3. And so let me show it. We have the Jupyter, which opens in a browser. And let's go to the upper right corner. The upper right corner. You see upload, new, and refresh. Let's click on new. When you click on new, perhaps on yours, you should see only Python 3, PyKernel, and R. Click on R, new R. And so when you do that, a new Python page will open, which is Jupyter. Let's see if it is ready for our class today. Let's see if it is ready for our class today. So let's type print, and then let's have a pair of brackets. And then let's have a pair of single quotes. You are going to notice that when you click on one of the brackets, the other closes for you automatically. And when I click on a single quote, the other closes for you automatically. So let's type into that. Welcome to the computational statistics class. Welcome to the computational statistics class. Now, this is just code. So you have to run it. To run it, you click on the Shift key and then you press Enter. That is the Shift key, and then you press Enter. When you do that, it should print for you, welcome to the computational statistics class. And so if this works, that means your system is ready for today's class.
Sorry, Professor, could you repeat the last part? So I put enter, but I don't know if I'm doing well.
No, you have to hold down the Shift key before you do enter.
The shift key, so.
The Shift key on your keyboard is to the left. Yeah.
Shift
and then you do
enter. Yes.
Exactly. Did it work? Did it work?
Yes, but I can't see the one number.
That is from here. From here,
okay.
You do print, then into bracket,
okay.
Then into single quotes, and then you type in, welcome to computational statistics class. And then you hold down the Shift, and then you press enter. If you don't get it, don't worry. We are coming back to it.
May I ask a question, please?
Yeah.
Yeah, I just realized that it works even with double quotes.
Come again.
I'm saying it also works with double quotes.
Yes, so of course.
Instead of single quote, it works. But then what's the difference between Anaconda 3 and Anaconda Navigator? Yeah, because when I installed, instead of getting Anaconda 3, I got Anaconda Navigator.
They might just be the same thing. They might just be the same thing.
Okay, thanks.
Yeah. And so once this is working, it means we are ready to start our class. All right. So my name is Korkpoe. I'm a senior lecturer in the Department of Finance at the University of Cape Coast Business School. Welcome once again to this class. Now let's take an overview of what you mean by computational statistics. We have statistics, and computational statistics is a branch of statistics. It's a branch that is concerned with the development and use of computer algorithms that provide numerical solutions to problems in statistics that are analytically difficult or intractable to solve. And so I've highlighted 3 terms here: computer algorithms, numerical solutions, and analytically difficult to solve. I'll be explaining these terms very, very shortly. And so problems to which computational statistics is used to find the solution include optimization, resampling, numerical integration, and the simulation of random processes or variables. In optimization, for example, in a manufacturing process, we want to be able to achieve our manufacturing at a minimum cost. And in resampling, that is what we do as statisticians or researchers. You know, when you have a research question, that automatically defines your population for you. But as you know, because of problems of money, time, and other resources, you cannot pull the whole of the population. You cannot pull the whole of the population. And so you have a sample. But one single sample, your findings on it, you cannot use it to represent what you found for the population. And so you have to do what you call resampling. The single sample that you have, hopefully, if it is representative of the population, then you can resample it. You can resample it, and it will give you values that are roughly what you are looking for in the population. And then you have numerical integration. It's an addition process. You come across that very, very soon. And then simulation of random variables, whether you want to simulate values from the normal distribution, the t-distribution, the hyperbolic distribution, and all those things. This is work for computational statistics. Now, when we say something is analytically difficult or intractable, well, this is just what it is. Real-life health problems are now performed on computers. And some of these things, the computation process is intensive with equally large data sizes. And so those things are not stuff that you want to give to pen and paper or your calculator. You really want a computer to solve it for you because it takes a lot of time. And these things move into what you call Bayesian modeling. Bayesian modeling uses Markov chain Monte Carlo. Or these days, there are other methods like NUTS, you have HMC, you have SMC, and so on and so forth. These are very large problems. large problems that you can't find an analytical solution to. And so you want to submit these problems to your computer. And knowledge of computational statistics is the beginning of solving those problems. Now we come to computer algorithms. An algorithm simply is, how do I move from step A to step B and then to my solution in step C? The problems that we are going to face, we have to give the computer clear instructions as to how it can get from A to C, what things it has to do in B. Sometimes it may have to repeat something. Sometimes it may have to branch. And so by algorithms, we just want to give the computer step-by-step instructions in arriving at our solution. And so the development of algorithms takes place through these processes. First, we are going to define the problem. And then we'll specify the algorithm. That is, we'll specify. And then we'll design it. And then you have to implement the algorithm. And in the implementation, you implement it in computer language. Whether it's C, it's C++, it's Python, it's R. You see, the specification and designing of the algorithm tends to be language agnostic. That is, I'm going to specify and design my algorithm not in any language. It is in the implementation process that we bring in a language. And then from there, we test. All things being equal, it should work. If it doesn't, we have to go through the process again. And so we'll start from inputs. We go through the process, and then we'll get output. Is our output what we want? If yes, we deploy the program. If no, we come back to look at the input again. So we keep going through this iterative process until eventually we get what we really want. Then we said the computational statistics deals with numerical problems. It deals with numerical rather than analytic. In analytic, you know that 5 + 6 = 11. In numerical solutions, we don't have the straight path of moving from a problem to solution. But what we tend to do is we find an approximate solution. An approximate solution that is just good for our implementation. You take an example. Look at airflow through the respiratory tract. It goes through curves, the air goes through corners, and so on and so forth. It's very difficult to map the path of the air. And on that basis, finding a solution. Some of the places, we are just going to say it's a curve, a smooth curve. But you know that in actual fact, the respiratory system hasn't got smooth surfaces. And so we can only get an approximate solution. And once that solution is good enough, we implement it. And so once again, computational statistics deals with numerical problems. to solve analytically complex or analytically impossible solutions through the use of algorithms. Now, algorithm is just a step-by-step means of arriving at a solution. And so we have programming languages to actually implement the algorithms that we design in computational statistics. Lots of programming languages today. We have some which are proprietary and some which are open source. Now, the open source languages are the main languages used in programming computational statistics. When it comes to machine learning, data science, artificial intelligence, and its sub areas like deep learning, we use open source tools. And some of the open source tools include Julia, R, Python, Rust, lots of them, together with their databases. The languages that we'll come across can be classified into two. We have what is called the interpreted languages versus the compiled languages. A compiled language, you are going to write your code in a high-level language. And by high-level language, we are talking about the code looking virtually like English. And then you have a compiler, which compiles the code after it doesn't get any, or it doesn't find any errors in the code. And it compiles this high-level language into what we call machine language. Machine language is very close to the hardware of the computer. And then from there, you run. Because machine language is very close to the hardware of the computer, it runs very, very fast. Unlike interpreted languages, which will not compile straight to a machine language, but it will take the code line by line, line by line. And so it tends to be slower. But then if you are developing applications, interpreted languages are more productive because development of applications tend to be iterative. You do this, you see whether it works. If it doesn't work, you change it. If it doesn't work, you keep going back and forth until eventually you have your code running. And so compare interpreted versus compiled languages. Interpreted languages are slow, but then when it comes to production, you achieve more. Compiled languages are very, very fast. But when it comes to production, you tend to be relatively slow. And so we move straight to our interpreted language. We are going to have a look at R. The course says we should have a look at R and Python. I'm going to tell you, having a look at both languages is impossible. We've got to go relatively deep into one of these languages. Some other time, maybe we'll look at Python. So let's start with R. R actually is a program that has been built for statisticians. It's a language built by statisticians for statistical analysis. So R is your perfect platform for doing all statistical analysis. It is an open source language, which makes it free. As you are aware, you installed R, you installed Python without paying anything. And so it's accessible to all of us. When R started, it started as a relatively small community used by academics. Now it is an industry strong language. And so let's just look at some basics of R. R can actually be used as a large calculator. And so I'm going to bring up my Jupyter, and then we run this. Now, the reason why I made you use Jupyter is that the class is relatively fast. And so we cannot afford to be having errors. And when we stop to correct the errors, the time is going and so on and so forth. You can, the R that you've installed, you can just run code in R. But here's the thing. You tend to commit a lot of errors on that platform unless you are already used to R. And so by moving to Jupyter, you'll see once you click on opening bracket, it closes it for you. When you click on single quotes, it closes it for you. When you click on a curly brace, it does those things for you. Those are the source of errors. And so we want to minimize the errors that we commit. Again, Jupyter is now the tool of choice when it comes to programming, doing notes, and so on and so forth, as you are going to see. And so let's bring up our Jupyter. Yeah. Can you see the Jupyter on the screen?
No, Professor, we are seeing your PowerPoint.
Oh, wow. I'm trying to, no, let's see. Let me hold down. Okay, good. Yeah, can we see the Jupyter now? Okay. So this is the Jupyter. The Jupyter actually stands for, the JU stands for Julia. The PY stands for Python. And then the R at the end stands for R. And so if you look at my Jupyter new, I've got Julia, Kotlin, Octave, Python, and R. You can actually run all these languages, which are open source languages, in Jupyter. Now, the Jupyter has, oh, come on now. I'm trying to have both the Jupyter and then the PowerPoint on the screen for you. Well, okay. So when you start the Jupyter, it has a cell. The first code we typed it into a cell, which was cell 1. And cell 1 had a ring of green around it. When you do Shift Enter, you come to another cell. That is the cell on your screen. We type code into the cell. And if you want to run, we do Shift Enter, then it will run. Sometimes the code that we type mistakes. And when you type a mistake and then you do Enter, you have an error. This error is a syntax error. Every language has its own rules. For example, English has its own rules. And when you violate this English language, we say you've committed a syntax error. And so when you violate the rules of a computer language, you've committed a syntax error. Whenever there is a syntax error, we have to go and figure out what the problem is. And then we come back to run the code again. So let's just use R as a big calculator, And so let's type 1 plus 1. And then let's run. To run, remember, to run, you hold down the Shift key, and then you press Enter. So it says 2. Let's do 8 times 8 times 8. The times, we are going to use the asterisk in place of the times. Let's run. You do Shift Enter. And then you want to do 2 exponent 8. That is 2 raised to the power 8. You do 2, and then the exponent, use the curved sign, exponent 8. I believe locating the curved sign shouldn't be difficult. I use a Lenovo. So the curved sign is on top of the numeral 6. We run.
Sorry, Professor.
So let's do into bracket. When you press the first bracket, it closes for you automatically. 5 plus 2, then get out, bring curved 4. We are saying into bracket 5 plus 2. Let's get out of the bracket. Let's bring curved 4. So I run, I get this. Then let's do 5 plus 2 curved 4. Let's run. Now you see that the answers are different because on line 5, I had into bracket 5 plus 2. I jumped out and then I did exponent 4. So you have 2, 4, 0, 1. And then on line 6, on line 6. I have 5 plus 2. 2 raised to the power 4. It's going to execute the 2 raised to the power 4 part first. That is going to be 16. And then it will add 5 to get 21. R also has some free functions. R has some free functions. Let's have a function like log. And then let's bring, once you type the first bracket, it brings the second one for you, 100. Now stop here, don't run, don't run. There are 2 ways of running code in R or in Jupyter. The first one is what we've just been using. We've been using Shift Enter. The second one is you do Control Enter. Control Enter. So let's do Control Enter. And so when you do log of 100, that is what you get. And this log is what you call the natural log. Log to the power of E as the base. Now, having done Control Enter, you see that no cell has been created for us. So to create a new cell, press the letter B. The letter B as in baby. So I press the letter B. Oh, come on. B. When I press the letter B, a cell gets created for me. And so another B, a cell will be created, another B, 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 B. So now I have enough of the cells created for me. And so once again, there are 2 ways of running code in R, in Jupyter. Shift Enter. Shift Enter will always create another cell for you. And then there's another way which you call Control Enter. Control Enter would not create a cell for you. Yeah, someone is asking, how do you delete a cell? Well, you just select the cell and you do delete. That's all, it's gone. And usually when you type an error, you can just click back into the cell and you can just click back into the cell and edit. That's all. I said the Jupyter could actually be used for both notes and code. Let's type some notes on my line 8. Let's type some notes. Notes like this is the computational. This is the computational statistics training. This is the computational statistics training. Now, clearly, you see that this line has English sentence. It's just a prose. And so if you like, run it and see. So we hold down Shift and then enter. When you hold down Shift and enter, it brings out an error, which says unexpected symbol. This is, then it has the CAD below it. You see, this line in line 8 is not actually a code recognized by R, but it's rather an English sentence. If it's an English sentence, then we don't have to treat it as a code. And so let's go back into this cell. Let's go back into this cell. And let's come here. This drop down. Click on it to drop down. It says code, markdown, raw NB convert, and then a heading. So we want line 8 to be just a markdown. And so we click on markdown. That's all. It's not code, it's English. Oh, can students see? Can participants see the Jupyter?
Yes,
Yes, we can.
Yes,
Yeah.
sir, we can see very well.
Yeah. So
But
just
initially the drop down that also we were not seeing where you were
Yes,
placing
okay.
the text.
Okay. So you have, this is computational statistics training. There are other things here, like heading. When you do heading, it will change, as you can see. But we don't want a heading. We just want it to be a markdown for now. Okay, so leave it at that. And you can even do it as NB raw NB convert. When you do raw NB convert, it converts into a type of a file that you can put online for other readers to actually read. And so line 7 is a natural log. It's log to the base of E. Let's do log to the base of 10. Perhaps the logs that we are very used to, unless of course you are an engineer or scientist. Engineers, scientists, they are used to logs to the base of E. The rest of us, we use logs to the base of 10. And so let's do log base 10 of 100. In other words, we are asking ourselves, what should be the power of 10 in order to get 100? That should be 2. And so let's run. And let's do another one, which says square root of 7. Another one which says absolute value of negative 67. And so these are 3 functions that R gives us. In fact, R has so many functions that you'll be exposed to. And then you should be able to write your own functions. We are going to be writing our own functions as well. Now, there are so many data types in R, what you call basic data types. You can have numbers. Even in numbers, you can have integers, and then we can have numbers with decimal places. You can have a string, for example, your name. You can have a list. You can have matrices. We can have sets. Look, lots of data types, lots of data types. And so let's just have a look at some of the R types that we have. Let's type of, and then let's have A. Let's look at the type of A. Let's run. It says A is a character. Now, this is what we should bear in mind. Anytime we type something enclosed in single quotes or double quotes, R regards that as a character or a string. Anytime the entity we type is in single or double quotes, R regards it as a character or a string. A string is just a series of characters. Let's find out the type of 1. The type of 1. Let's do enter. It says it is a double. Now, R regards all numbers as doubles. That is, potentially numbers with decimal places. But you know, when we count, we just count from 1, 2, 3, 4. And so counts are integers. And then measurements. When I want to measure your weight, your height, your shoe size, those things are measurements. And so measures, we get double. And for counts, we get an integer. If we want to show counts in R, we've got to bring the letter L, capital L, at the back of a number. And so let's do type of, and then into bracket, let's say 58, capital L. 58, capital L. I hold down the shift key and press enter. It says it is an integer. It's worth repeating once more. Numbers in R can be integers or they can be doubles. Integers are the result of counts. They are discrete values. Doubles are the result of measures. They are continuous values. To get an integer in R, you have to bring L at the back of it, well, in front of it, because R regards all numbers as doubles. And so let's do type of and put in 1.3. When you execute, it says double because it is a continuous value. And so we have what you call arithmetic operators. The same arithmetic operators that we have in math, the same arithmetic operators apply in R. So we have addition, subtraction. When it comes to multiplication, the sign changes. That is, we use the asterisk in place of the times. Division, we use the forward slash. The forward slash. And then the power raised to the power, we used the curd. The curd. We don't use the this. It has a different meaning for people from engineering backgrounds. And so addition, normal addition, subtraction, multiplication, division, and then this is what we call raised to the power. Then we have what is called matrix multiplication. Something will be coming across soon. If you want to multiply two matrices, X and Y, this is the sign that you use. If you want to do modulo arithmetic, and then whole number division, this is what you use. And so bear these things in mind. We'll be using them very soon. We have what is called the order of operations. That is, if you have mixed mode arithmetic, where you have arithmetic operation, and then it has different operators. For example, can you see the slide anyway?
Yes, Professor.
Okay, yeah. So for example, this statement here says into bracket 5 plus 1. Then it raises something to the power 4. Then it divides. Then here you have subtraction, and then something raised to the power again. That is what we call a mixed mode arithmetic sentence. It's made up of addition, the exponential, multiplication, division. So it's mixed mode. When R wants to evaluate a mixed mode arithmetic, it starts from anything in brackets, that is parentheses. Then it goes to deal with anything that involves exponents. Then multiplication, division. Then you come to addition and subtraction. So multiplication and division, they are of a higher order than addition and subtraction. In fact, multiplication and division, they have the same order. Addition and subtraction are also of the same order. Therefore, whenever it comes across a sentence that has multiplication and division in it, it evaluates the sentence from left to right. The same thing applies to addition and subtraction. And so we are going to solve this problem in R. Before then, let's look at it and see if we can guess the answer. That is into bracket 5 plus 1, and then bracket close, raised to the power 4 divided by, into bracket 9 minus 2, bracket close, raised to the power 3. Let's just see if we can guess the answer. That should be 6 raised to the power 4. And that should be 7 raised to the power 3. So 6 raised to the power 4 divided by 7 raised to the power 3. Let's do it. Let's do it. And so into bracket 5 plus 1, get out. Come again.
Approximately 2.8. So.
Yeah, so let's do 4, then divided by this 9 minus 2 raised to the power 3. Let's run. And so 3.778 and all that. What the R did was to evaluate the guys in bracket, and then it raised to the power, and then later it came to do the division. And so for mixed mode operations, the short name is PEMDAS, which is parenthesis, exponential, multiplication, division, addition, and subtraction. We can do what we call conversions. That is, change a value from one type to the other. Let's type. And so let's have my int. And very soon you understand where these names are coming from. To be an integer. Run. And then let's have my double to be a double. A double is 3.2. Let's look at what has been stored in my int. We'll come back to that very, very soon. So you do type of, and then you type my int. We run. It says it is an integer because I've got R at the back of it here. Let's do the same thing for my double. It says it is a double. We are going to add an integer to a double to see what type it will give us. An integer to a double to see what type it would give us. So we do my sum. Oh, my sum is assigned my int plus my double. And again, when you are typing the names of the objects, remember R is case sensitive. And so if you have my double here, when you come here, you change it to a small d, it will throw out an error. If you have my int, if you come here and type it as a small I, it will throw out an error. And so remember, R is case sensitive. Let's run. And so we have an integer and a double. They are different data types. R does not allow operations involving different data types. And so let's look at what it does. So let's do type of, and then let's do my sum. It says double. And so this is what happened. This is an operation involving an integer and a double. R will implicitly promote the integer to a double before it's able to add a double to it, and then store the value in my sum. That is why my sum gave you double. And so we can actually promote values to different types of data types. We'll be coming across what we call logic. And logic has two values. Something can either be true or it can either be what? False. We call those data types logical values, true or false. R regards 1 as true and 0 as false. And so let's do it. Let's do type of. And inside it, let's type as logical. And then have another pair of brackets. Let's put here 1. Let's run. It says logical. logical. And so this in the ordinary R is a double. But you want to convert it into a logic value. How do we do it? We do as dot logical. And then we layered on it type of what it says is logical. So try this. Logic is assigned as dot logic into bracket 1. Let's run. Oh, logical. Run. Logical, run. And then let's see what we have in logic. Let's run. It says true. Let me remind you, this sign, the name of this sign is, the name of this operator is the assignment operator. It is not equal to, no. It is the assignment operator. So here we are saying evaluate as logical into bracket 1. Whatever you got, assign it to logic. So it has nothing, absolutely nothing to do with equal to. The equal to operator in R is double of the equal signs. This is the equal to operator. And so it's not code. I'm going to make it this and have another cell. Let's do an experiment. Let's do an experiment. Let's do an experiment. We know that 2 times 5 in mathematics equal to 10, right? 2 times 5 in mathematics equal to 10. Run it and see. 2 times 5 equal to 10. Run it. When you run, you should have an error. When we run, we should have an error. Error because this sign, the interpretation is different from the interpretation in mathematics. But when we do 2 times 5 equal 10, do it, let's see. 2 times 5 equal 10. We run, you should say true. And let's try 100 equal 6 times 14. Okay, 6 times 10. This should give us false. And so once again, there is a difference between this and this. The first one is just saying, evaluate what you have on your right-hand side and assign it to the left-hand side. The second one is testing whether the left-hand side equals the right-hand side. This exists in all languages. But a single one is just saying assign the right-hand side to the left-hand side. And the double is saying something is equal. Bear this in mind. So object types in R, we started with some object types. We saw the integer, we saw a double, we saw a character. In R, everything is an object in R. Why do we need to know about objects? Well, what R does is it reads only objects. It can modify these objects, produce another object, and also call on existing what? Object. Maybe this will not mean much to you for now, but as we go on, we'll come back to this particular slide, and then you get to understanding. And so objects that you can come across in R include vectors. They are not vectors in mathematics. So if mathematics is not your thing, don't worry. It's not vectors in mathematics. Then you come across what you call matrices and arrays. Data frames. You come across what is called lists, factors, and actually functions. We'll be looking at data frames. And a data frame is an object that looks like Excel. If you take Excel, it's made up of rows and columns. That is the way we capture data. And then we are going to be reading into our R. List is said to be a container. If you take your bag, wherever you are now, in your bag, you have different objects. Maybe you have books, you have a calculator, you have a pen, you have a pencil, maybe you have money. So a list is what we use to store different types of objects. And of course, the data that we go to collect, that is the nature of the data. We'll collect wage, we'll collect educational level, we'll collect gender, and so on. These are different types of what? Objects. And so we are going to collect them in lists. Then we come to factors. It's not all objects that you come across in R which are numbers. Some of them are said to be factors. For example, someone can be male or female. Someone can survive a treatment, or the person can die. You can have other things like low income, middle income, and high income. These are factors. Then you come to functions. Of course, we saw some functions a couple of minutes ago. Log, square root, absolute, those are functions which are inbuilt into R. We'll learn to write our own functions. Learning to write your own functions is actually the beginning of computational statistics. If only you can just have a problem and learn to logically write your own function to solve the problem, I tell you, you are up there. And so a vector is a collection of objects of the same type. Let me repeat that. A vector can only hold objects of the same type. Let's say numbers, let's say names, let's say doubles. It cannot mix the types. It can only hold objects of the same type. And so let's form a vector. Let's form a vector. To form a vector, you only need the keyword C. The keyword C, and then you bring a pair of brackets in front of it. And so let's have V1 to be assigned a vector C. Whenever you see this, the pair of brackets, it means whatever you are using is a function. Let me tell you before we go to functions. Whenever we find a pair of brackets in front of whether it's a word, it's a letter, we are dealing with what we call a function. And a function is any structure that takes the inputs through some processing and then gives you an output. Any such thing, we call it a function. It takes an input and then does something to the input to give you an output. It's called a function. And our functions will always have a pair of brackets in front of them. So I have a function here, and this function is called a vector. I'm going to put some logic figures in it as what? Inputs. So let's have true, comma, and then space, false, comma, space. Let's have true. They are all in capital letters. They are all in caps. And we are going to be making use of what you call white space. White space. That is, I type true, and then I bring comma, and then space before false. Then I bring comma, space before true. That space, we call it white space. It is just to enable us to read whatever we typed conveniently. And so whether you bring space or not, you don't have an error. But the spaces are necessary in order for us to read conveniently. And so let's execute. And then let's spell. Let's spell. What happened here is V1 has been assigned a vector of true, false, true. These values have been stored in a variable called V1. When I spell V1, I get the values that have been stored in the variable called V1. Let me touch briefly on variables. A variable is just a location in your computer's memory that stores objects for you. Imagine I did this and press enter. It gives me yes, true, false, true. But suppose I needed it to add to something. I don't have anything to hold on to. But here, having done V1 is assigned. Remember, is assigned the vector of true, false, true. Anytime I need these values, I just refer to V1 and then I have it. And so variables are used to store objects. Variables are used to store objects. We can give a variable any name at all. We are allowed. But when you are giving variables names, the names have to reflect what the variables will be doing, so that next time you come back to your code, it's easy for you to know what you are doing. And so suppose I want to store the heights of students. I can say H is assigned a vector, heights of students, let's say 1.82, 1.55, 1.65, 1.90. This is a vector of the heights of students. When I run, yes, it runs. If I want the heights, yes, I have it. But how will I know that height is represented by H? How will I know? Calvin, I think Calvin,
Hello, Doc.
I think it's break.
Oh, okay. I believe so.
10,
Do you want 30 minutes or?
those objects. And then those objects are given to us. And if you want to name a variable, you can give it any name at all. Any name. But you see, when you write code, the code is going to pass on to some other person to be maintaining it after you are gone. And so make the work easier for the person by making your variable names contextual. That is, the variable name must say what the variable is doing. So if you are storing height of students, why do you use H instead of height? If I'm going to compute the average mark of students, I need to do it average mark of what? Students, instead of S or A. So average mark of students, I might do average mark of students. This variable name more or less communicates what is going to what? Store. Average mark of students. So I say average marks of student is 78.9. The moment I say it, I know that 78.9 is what? Average mark of what? Students. Better still, I could make it average. Well, I could make it average underscore mark underscore of underscore students equals 78.9. So any of these variables actually portrays what I'm storing in it. Than just going to say X equals 78.9. It's also going to run. But see, if you give the code to someone to be maintaining for you, and then average mark of student is 78.9, and then you come and call it X, how will the person know that X has anything to do with what? Average mark of what? Students. And so, listen to me. All our variables have to be in context. The variable name must say something about what the variable is actually what? Storing. Variable names can only be alphanumeric characters. Alpha and numeric. And so I can call a variable num1 to store 64, num2 to store for me 79, and then num3 to store for me 56. The variable name is alphanumeric. The alpha is NUM, and numeric is 1. A variable name cannot contain spaces. So this one will do this. And then I can come and have a variable name num1 to be 64. No, because it contains what? A space. A space. That will be an illegal variable name. So when you run it, it says error, because it has what? A space in it. A variable name cannot start with a number. So I cannot have this. I cannot have this. I cannot have 2 height equal 89. I cannot have this. I have 2 height equals 89. I cannot have that because variable names are supposed to be alphanumeric, not numeric alpha. So here you have a number starting a variable name. That is an illegal variable. So it will throw out an error. And you can have strange characters in between your variable names. You saw what I did here. You saw what I did here. I did average underscore mark underscore of underscore students. It accepted it. Let's do another one. And then to have average dash mark dash of dash student. And then of students, let's say 100. And run. It says there is what? An error. So the only thing you are supposed to have in the names is an underscore. Underscore. And then we have what is called a naming convention. A naming convention. Suppose you are in India and I'm in Ghana. We are working on a project. That's okay. Develop this part of the project. Let me also develop this part of the project. How do we name our variables? We can adopt a means of naming them. And one means of naming them is what we call the camel case. The camel case. And you know the back of the camel, it goes like this and then like this. So in the camel case, if I want a variable called animal, I'll say, okay, camel case. Oh, come on. Camel case. And I'll say, okay, is a camel. Camel case is assigned a camel. Where do I have the camel case? In camel case, you start your variable names with lowercase. And then any other word, you start with uppercase. There is no space between the words. So number of students. I'm going to do it number of students. Number of students. Look at it. I started with what? Lowercase. Then the next word is of. Uppercase. Next word is students. Uppercase. Number of students, 35. And then I do this. And so this is what you call the camel case. And usually at the start of the Oliver Kimaro, you are disturbing the class. Usually at the start of your project, you've got to agree on which convention you are going to adopt in naming your variables. And so I could have another variable. Let's have another variable. Let's call it V2. It should be a vector of strings. Let's put in the first string to say hola. Oh, come on. And the next one to say howdy. The next one to say hello. Oliver Kimaro, you are disturbing the class. And so we have a vector of strings. And strings should either be enclosed in a single or double quotes. I prefer single because for a single quote, you don't have to hold down any key before you press it. And so let's run. Let's run. Let's look at what is contained in V2. That is it. That is a vector. Let's have a vector of numbers. A vector of numbers. Let's call it V3. V3 should be 1, 2, 3. 1, 2, 3. Run. And then let's spell V3. It says 1, 2, 3. You can have different arrangements to enter your numbers. You can have different arrangement to enter your numbers. For instance, we can have V4 to be the vector 6 to 10, and then 27 to 49. No, that's too much. 27 to 35. You have 6 to 7 first, and then 27 to 35. Let's run. And then let's spill out. And so we had 2 segments. That is 6, 7, 8, 9, 10. And then from 27 up to 35. These are all vectors. We come to matrices and arrays. A matrix is just a rectangular array of numbers. And when I say a rectangular array of numbers, it won't even communicate very well what a vector means, a matrix means. Look, let's do a matrix here. So we have a matrix of drugs, vitamin A. Then, oh, come on. Vitamin B. And then vitamin C. Let's call it region or district. Let's call it district. Or district 1. District 2. And let's have district 3. So we have district 2. Oh, come on. 2. And then here we have 3. Look at it. We want to supply vitamins to the district hospitals. And so for district 1, let's say you have 5,000 pieces. District 2, let's have 2,000 species. And then district 3, let's have 4,000 vitamin C tablets. Let's come to district 2. Vitamin A, let's give them just 1,000. Let's give them 500. Perhaps it's a very small district. And let's give them 1,200. District 3, which is very large, let's give them 10,000. Here, 8,000. Oh. And finally, for C, let's give them 5,000. Look at this chart. So district 1 had 5,000 vitamin A, 2,000 vitamin B, 4,000 vitamin C, and so on and so forth. This is a matrix. This is a matrix, which we define as a rectangular array of numbers. And so matrices in mathematics are not, strange. This is just a matrix. And we could have another matrix, which will be the cost per vitamin. And so we can have total cost. So it's not code, it's English. I do this. This is a matrix. So matrices exist in R. They exist in R. Let's capture our first matrix. And for matrices, matrices who have both rows and columns. The rows are the districts and the columns are the respective vitamins. Let's see how you do it. So call it matrix 1. Let's call it matrix 1, 1. Everyone should be typing. And we use the keyword matrix. It's a function. So you bring this. And then we pass to it a vector. The vector is 2, 0, 1, 3. And then we jump out. We jump out of the innermost function and we do comma and then this. Then we do number of rows. N row. We want it to be 2. Then N column. We also want it to be 2. This will give us a 2 by 2 matrix. That is 2 rows, 2 columns. Let's run. And then let's spill. That is it. Do we have it? Do we have it?
Yes.
Okay. So
I have a question.
I got an error.
you got an error.
Yes, I did.
Okay. So let's go back again. Let's go back again. We have matrix 1. There is no space between the matrix and 1 because it is a variable. Should be assigned matrix. And then when you open this bracket, Jupyter closes it for you straight away. And then you type in the vector C, then you open, it closes it for you straight away. Then you type 2, comma, space 0, comma, space 1, comma, and then space 3. And then jump out of this bracket and this bracket. And then you bring a comma. And then space. N row 2, comma, space N row 2. So you want a 2 by 2 matrix. Did it work now? The participant who said she had an error, did your code work now?
Not yet.
Ooh.
Trying to correct myself.
Okay, for the rest, did it work?
Yes, it worked.
Okay, so when you do it and then you type matrix, it gives you this. That is a 2 by 2 matrix. Let's have another matrix and call it. So follow closely, follow very closely, because this is not in person, so follow very, very closely. Don't let us leave you behind. Matrix, and then you do this. You bring C, you do this. They bring 5, 7. You jump out. You do number of rows to be 2. Now R is able to figure out. You've got just 2 values and you say number of rows 2. Yeah. Let's run. We run. And so we are going to do matrix multiplication. We are going to multiply our matrix in matrix 1, 2, matrix 2. Let's spell out matrix 2. That is a 2 by 1 matrix. So we are going to multiply them. To multiply them, you use the operator, which is percentage star percentage. That is what you use in multiplying matrices. And so let's have matrix 3 to hold our multiplication. Is assigned matrix 1, matrix 2. Sorry, I have to type slightly fast so that we can cover whatever we want to cover. And so let's run. When we run, it's multiplied for us. We've multiplied this matrix 1 by matrix 2, and the answer has been stored in a variable called matrix 3. Let's spell matrix 3. Do we all have 1721 as the answer?
Yes, teacher.
Yes.
Okay.
Yes.
Okay. So let's have a new one. Let's have a new one. Let's have a matrix A. Sorry, capital A should be assigned matrix. And let's have this. And then let's have this. Let's put in values. -1, 4, 3, 3, where are you? 3, 2. Let's make it number of rows to be 2, number of columns to be 2. Let's run. Once we run, let's spell A. So this is what you have. let's have B. Let's have B, a matrix B to be matrix. If I'm too fast, you've got to stop me. Huh?
It's fine.
B
it's
to be
fine.
5, 2, -3. Well, let's have a number 1. Let's also make it 2 by 2. So n rows, n row to be 2, n call to be 2. Let's run and spill out B. We want to multiply A by B and store the results in C. See if you can do it yourself. You want to multiply A by B, and then the results should be stored in a matrix called C. That will be A is assigned, sorry. C is assigned A multiplied by B. We are multiplying A by B, and then the result stored in C. Let's run and see. There we go. And let's spill C. There we go. Do we all have this C with elements 1, 6, 24, -10?
Yes, teacher.
Okay, thank you. So let's go on. You have to do this by hand, and then you try it through R and see how it plays out. We can also have what you call 3-dimensional arrays. 3-dimensional arrays. You see, when we did this, look at it. When we brought these vitamins, we could also have brought to it the supplier. So for district A, who supplied the vitamin? For district 1, who supplied vitamin A? And then vitamin B, and then vitamin C. We can also bring with it the regulatory body that certified these vitamins. And we can also bring with it the temperature at which the vitamins are to be what? Stored. And so we can have what is called 3-dimensional arrays. 3-dimensional arrays. Can you see the slide?
Yes, Prof.
Yes.
Okay, so with 3-dimensional arrays, you have a matrix 1, and then behind it you have a matrix 2, behind it you have a matrix what? 3. These are the matrices. These are the matrices 1, 2, 3. And so we arrange it 1, 2, and then 3. They are called 3-dimensional arrays. 3-dimensional arrays. And you can just capture them as you see in the slide. That will be left for you to actually do. We now want to talk about lists. We now want to talk about lists. A list is a container. And an example of a container is your bag. Your bag near you will have so many items. Maybe you have water, you have a book, you have a pad, you have your spectacles, you have your pen, you have your pencil, you have your calculator. And so a container can hold a lot of information. When you take a database of a patient, you store the patient's name, the amount of bill due that the patient has to pay, and whether the patient has insurance or not. Look at the data types. Name is a character. Your name is always going to be a character. The amount that you have to pay is going to be a double. That means it is numerical. And then whether or not you have insurance, that is going to be a logical, because whether or not you have insurance is either going to be answered by yes or no. Yes or no. That is true or false. We can combine this information into a collection that we call a list. And so let's create a list. To create a list, the keyword is list. Let's create it. Let's create a list. So let's say our list is called patient. And we are creating a list. It is a function. And so you bring the pair of parentheses. Let's call the patient Angela. And then it is a patient's name. So it's a string. Therefore, I have it enclosed in a pair of single quotes. The amount Angela owes is 75. Well, cedis, dollars, whatever. And whether Angela has insurance. Yes, it's true. She has insurance. And so take note here. A list can contain different data types. You have character. You have a number, which is numeric. And then you have logical. Unlike a vector can only contain one data type. And so run. After running, let's see what is stored in patient. Let's see what is stored in patient. What is stored in patient is name, Angela, amount owed, send 5, whether or not Angela has insurance. Then we are saying it's true. There are basically 3 ways of assessing the information contained in our list. The information contained in our list is Angela, the amount owed, and then whether or not Angela has insurance. Let's see how we can assess this information contained in the list. The information that is contained in the list is stored in a variable called patient. And patient has Angie send 5 true. So suppose you want Angie. One way of doing it is we'll do patient. Let's type patient, and then you bring the $sign. Patient, and then the $sign. And then you do name. Patient, the $sign, and then name. Run. It will give you Angela. And so how can we assess this, whether Angela has insurance or not? You do patient, $sign, insurance. Insurance. You run. It says true. That is one way of assessing information in a list. Another way will be to type the name of the variable. To type the name of the variable. So let's have patient. Then we bring the square brackets. The square brackets. We bring another one, square brackets again. And then we want name. Name is a string. So we bring this. Then we type name. Let's get used to this. When it comes to our data analysis, we are going to be using it. Let's do this. And then it says Angela. That is another way. And then the last way, the last way is we'll bring a number where the number is the position of whatever we are looking for. So look at this again. Oh, come on. Look at this again. Name, Angela. Amount owed, 75. Insurance, through. Their positions are, name is at position 1. Owed is at position 2. Insurance is at position 3. This is the difference between R and Python. R starts counting from 1. Python starts counting from 0. So this is 1, 2, 3 in R. In Python, it would have been 0, 1, 2. And so suppose I want to know how much Angela owes. That will be 2. So I come back, and I put in 2. Come back and I put in 2. So when I run, it says 75. And so in short, there are basically 3 ways of assessing members of the list. It can either be you do the name of the list, and then you bring the $sign, and then whatever entity you want, you bring it, it will spell it for you. You might bring a number, or you might bring the name of the entity. It's very simple. Here, you call the two an index. And so name of a list, index 2, will give you what Angela owes. Name of a list, index name, will give you Angela's name. And so these values that we have in here, they are just called indices. An index, or plural, indices. So you go through this part. We can add and remove something from a list. I mean, think about it. Your bag. You can take out a book. Or if it's money, you can add money. If it's water, you can add water. So I'm going to spell out patient again. Patient again. Let's look at patient. It has name, amount owed, whether or not Angela has insurance. We forgot one thing. That is Angela's age. So you want to add the age of Angela. All that we got to do is patient. Then we bring the $sign. $sign. And then we say age. Let's say Angela's age is 27. We are adding. It's like you put another thing into the container or the bag. Let's run. And then let's see what you have in patient. Now it says you have name, amount owed, whether or not you have insurance, and then age. And so we have 4 variables now in our list called patient. Suppose we want to take out something. We want to take out Angela no longer owes money. She's paid, or her insurance has taken care of the amount she owes. All that we have to do is patient, and then we'll bring owed, the amount she's supposed to owe, and then we bring now. Let's all type. I know when you are teaching, and then some students hate to type code. Let's all make the effort to type. This thing is not difficult. And if you're able to type code, you are through. So let's run. Amount owed, we've made it null. Let's now see what is in patient. You can see that the amount owed has been taken off. Any questions at this stage? And I know most of you. Yeah. Now how?
Can you please come at the number 50?
Number
50.
Okay.
Where you are talking about the matrix.
Yep. Now, go ahead.
Yes. Here I'm asking how you give the number, like you write it down 2013. How we can take this number?
Okay. So
yes.
It's okay, let me make it here. Boom. Okay. So it arranges the numbers by row. Oh, come on. By row or by column. So the default is by row. By row means it will do 2 and then go below 2 to put 0, and then comes back to 1, goes below 1 to put 3. That is by row. But if it's by column, it will do 2, go to the next column and put 0, and then come under 2 and put 1, and then put 3. So the default, all the functions have default values. And the default values for matrices, when it comes to arranging the numbers, is by row. But we could have changed it and make it by column. We are allowed to. Has your question been answered?
Yes, Professor, thank you.
Okay. So if you want by column, you just do by column to be true. You just put it somewhere here. That's all. But by row is the default. And so you don't need to actually bring it. So let me make this place a markdown. Good. Any other question before? Come again. Okay. So that is just about lists. You can have names. So when you have a list, and you see this list is a rather simple list. This list is a rather simple list. So we know the variables are name, insurance, and age. We are going to be seeing data that contains a lot. You cannot know the names of the variables. And so to know the names of the variables, you use R's function called names. Let's type. We use R function called names. And then in names, let's bring patient. And run. It gives you the names of the variables that are contained in our list. And so we are going to be loading data into R. The first thing we want to know is what are the variables? We'll just do name, the name of the file that we loaded, and then it will give us the names of the variables. When it comes to functions, we have some functions that we apply specifically to lists. And they do the work for us very easily. The first function is called apply. And then we have others like list apply, and then the S apply. The original apply, we could specify to find something like mean, median, mode. Then it will do it for us. So let's find it straight away. Let's have a list of numbers. So let's call it N should be assigned a list of numbers. And let's have our numbers 1, 5, and then 6, 37. We have two lists in this list. So a list can even contain another list. It's allowed. Let's run, and then let's spell N to see what we have. And so the first list, we have numbers 1 to 5. The second list, we have numbers from 6 to 37. And so this is a list in a list. Let's find our first list. It's the first list. Let's run it. It says 1 to 5. our second list. It says 6 to 37. This is a case where we have a list within a list. Let's apply. Let's apply. Let's use the R function L apply. R function L apply to the list for us. It's a function. And if it is a function, you've got to bring the pair of parentheses or brackets. Let's pass to it our list N. And let's see, find the median for us in the list. Find the median for us in the list. Remember, you have two lists. The first, and then the second. And so when you say list apply to the list of the median, it's going to find the median for the first list and the median for the second list. Let's run. So the median, don't forget, the median is when the values are arranged in increasing order. The first list, the median is the middle number, which is 3. That is it. And then the second list is 21.5. So when you count from here and then you count from here, you get to 21 and 22. And so you find their mean, that will be 21.5. Try finding the mean. Let's see, the mean. The mean. The mean. Try finding the mean of these lists. Let's see. One moment. The air condition is way too much. Yep. Have we found the mean?
Yes,
And
sir.
so all that we do is L apply them N, and then we do the mean. That is it. Let's find the standard deviation. Find the standard deviation. Let's find the standard deviation. So L apply, boom, boom. We pass, then we pass SD, I believe. Yeah, that is it. And so by giving the list, and then we call given functions, it will find all those for us. Granted, they make sense. Granted, they make sense. The same thing with sapply. Sapply would actually return a vector. If you look at this, it returns individual values. But if you do sapply, and then let's give it mean. When we run, it returns a vector. Unlike here, where it returns 1, 2. Here, it just returns a vector. We have what we call recursive lists. That is a list within a list within a list. So that is left as an exercise for you. Let's work with numbers now. Numbers. Lists which are numbers. And so here, we are going to generate a series of random values. I believe most of us have studied statistics. We know what is called a normal distribution, isn't it?
Yes.
Yeah.
Okay, so let's generate some random values from a normal distribution with a mean of 10 and then standard deviation of 13. So let's type X is assigned random distribution. A random distribution is R norm. R stands for random, and then norm stands for normal distribution. We want to generate 500 values from a distribution with mean 10 and a standard deviation of 3. That is, you want 500 values from a normal distribution. Let me just show it. Let me show it. Let me show it. Normal distribution, normal distribution, distribution. And normal distribution. One. Boom, boom, boom. Boom, boom, boom. I'm just picking a normal distribution for us to a normal distribution. Okay, good, got you. Copy image. Computational statistics. Oh, too small. Okay. Can we see the slide on board?
Yes, Prof.
Okay. So suppose these are the incomes earned by those of us taking this class right now. The minimum income is 10. The maximum is 140. And so people who earn 10, how many are they? Come and stand here. People who, so those of us who earn 10 will come and stand here. 140 will come and stand here. And for the rest of us, the amount of money that you earn, you come and stand on a particular line. So if you earn 40, you come and stand here. If another person earns 40, the person will stand behind you. And that person, the person will stand behind you. This is just what you call the distribution. And distribution is actually nothing strange. This is what it is. The lower earner, the upper earner, and the rest of us come and stand. If you stand and someone also, and the person should stand behind you. And when we draw a curve around our where we stand, around our heads, this curve here is called the normal distribution curve. And the middle will give us our mean. In this case, we want a mean of 10 and standard deviation of 3. So the mean here is supposed to be the middle of 10. The standard deviation of 3. So 10 plus 3 will be around here. 10 minus 3 will be around here. And so for this picture, we want 500 values. Anybody standing on this line has an income of 70. Anybody standing on this has an income of 80. All we want 500, but we want them randomly. So we can just come and pick somebody. Then we note how much the person earns. Then we say, go back and join these people. Then again, we come and pick somebody. We note the person's income. We say, go back and join. We are going to do that until we come up with the 500th person. So that is all that we mean by this statement. X should be assigned random values from the normal distribution. Pick out 500 values with replacement. That's when we pick you out, we note how much you earn. We ask you to go and join the people, and then we shuffle and pick another person out. The mean should be 10. The standard deviation should be 3. So let's go back to our Jupyter. Excuse me. And so let's run. $500 varies from, so I'm going to write it down. 500 varies from the normal distribution with mean with mean mu. Oh, with mean equal to 10 and standard deviation equal to 3. And so it is a markdown. Let's look at the values that have been stored in X. So you do X, and then you spill. You do X and spill. These are the values. These are the values. These are the values. 500 of them. And you are going to have values that are different from what I have, because we said the numbers should be randomly generated. And so 500 values. Are you able to do this?
Yes, Prof.
Okay, thank you.
Can you please go back to the code? Sorry.
The code is yeah, I'm here now. X should store 500 values from the normal distribution with mean of 10 and standard deviation of 3. And when you spill the values, that's what you are going to have, a lot of values. That is X. So let's generate Y. Let's generate Y. So Y will be 3 space star X space plus. Again, we have the normal distribution, 500 values should come from normal distribution with 0 mean, and then 2 standard deviation. We are generating both X and Y values. This is called a simulation. So we simulated 500 values from a normal distribution with a mean of 10, standard deviation of 3. And then we are simulating the corresponding Y values using this equation, which says multiply 3 by X and then add 500 values generated from a normal distribution with mean of 0 and standard deviation of 2. So I generated. This time I'm not going to spell it because that is going to be too much for us. We want to form a simple linear regression. We'll be coming to regression big time, but we just want to use this to illustrate the concept of lists. So to generate a linear regression in R, it's just as easy as that. Let's call it fit, and that should be assigned LM. LM stands for linear model. All in lowercase. Linear model, and then let's have Y space, and then we have tilde X. the tilde, I use a Lenovo, so the tilde is below the escape. The tilde, have we got it?
Yes, sir.
Yes, sir.
Okay, let's run. When I run, it fixes the linear model for me. And let's spill whatever we've got. After running, we spill fit. So we did the linear model. We stored it in fit as a variable. And then we want to know what is in fit. What is in fit? It calls out the equation. You remember this. The equation we had is LM, that is y tilde x. And then it's going to bring out the coefficients. That is the intercept value and then the x value. I'm saying we are not supposed to have the same values because we are using random values. When we have a linear model and it gives us whatever it contains, it's always a list. And let's have a look at that list. So we do summary. Summary. We do fit. Summary. Function. Fit. Let's run. When you run, you have all this. A list containing the residuals. Don't worry if you don't understand it. This is what we are doing today. So we'll get to understand all this. So you get residuals, you get the coefficients, then the significant codes, residual error, multiple R squared, and adjusted R squared. Then you have F statistics. This is all lists. And the list has members, residuals, coefficients, significant code, residual error, standard error, multiple, and so on and so forth. So we'll be coming across this particular thing. I'll explain what all these numbers mean, and then we go ahead. And so let's look at the names. Let's look at the names. It was called fit. So let's look at the names. Let's look at the names contained in fit. Am I too fast or you are following?
Yes, following.
I'm following on my side.
Okay.
I'm following.
Thank you. So the names contained in fit are coefficients, residuals, effects, rank, fitted values, right up to what? Model. Let's look at the type of object of fit. So we do type of, and then we do fit. It says fit is what? A list. And so even data that we have, the data is made up of what? Lists. Therefore, lists are very important in R. We will be coming back to lists again, and you'll get it. Let's come to data frames. Data frames. A data frame is one of the important objects to us as data analysts, to us as researchers. The data frame is nothing more than an Excel sheet. That is how a data frame looks like. And it's made up of rows. And the rows are the observations. And then columns. The columns are the variables. And so suppose I'm looking at my lifestyle. I'll have my name, my age, my diet type, my BMI. That row will contain facts on me. And so we call it a case or an observation. And then the columns will be name. So my name will be there. Age, my lifestyle, my BMI, my income. These are variables. And so when we combine rows and columns, we have what is called a data frame. Let's just create a small data frame to see. Usually, data frames, you have created them in Excel or any other tabular format and load them into R. And that is what we are going to be doing. So just as an exercise, let's create one, and then we see how it plays out. Later, we'll be loading data from our hard disk into R. And so let's create a vector of names. Let's create a vector of names and assign it names. That is Angela, and let me look at the name properly. Chandra. Angela and Chandra. Don't run. Don't run. Angela and Chandra, just do enter. When you just do enter, it will not run. It will just move to the next space. And then ages. The ages, let's capture it as a vector and do 27, 36. Again, don't run. Just do enter. Let's do insurance. Let's capture it as a vector. And let's do true and T. Okay. So we have 3 statements which say name is captured as a vector. You have name Angela and Chandra. These are strings or series of characters. So they've been enclosed in single quotes, ages, and then whether they have insurance or not. Let's now run. Let's click in it and run. So we are going to combine these 3 vectors into a data frame. And so let's call them patients. That should be assigned data dot frame into bracket names, ages, insurance. Yep. Let's run. We have our data frame created from the vectors, names, ages, insurance. And we are combining them into data.frame. Anyone able to get it right? So you want to see your data frame. What is stored in patients? You do, and this is what you have. Do we have the same thing?
Yes, sir.
Yes, I do.
Yes, Professor.
Yeah, thank you. Let's see whether it's indeed a data frame. Let's do type of patients, type of function, patients. Run. Okay. So it says your data frame is made up of what? Lists. And let's do class patients. Patients. Class patients. And run. It says it is a data frame. So your data frame is made up of what? Lists. These lists are names, ages, whether or not you have insurance. You notice one thing here. True and T did not complain because it understands that T stands for true. And so you did the class and it says it is a data frame. And so we can add, if you look at it now, it's made up of 3 columns, 1, 2, 3. And rows, 3 rows. The first row is the names. The second row is Angela. Angela is 27 years. She has health insurance. Sondra, 36 years. She has health insurance. Suppose we want to add another row below here, or another column. R provides us with functions that we need to use to carry out this very easily. These functions are what you call R bind and then C bind. R bind means row bind. C bind means C column bind. And so when we R bind with something, it's going to come to the row. When we C bind with something, it's going to come with what? The column. Let's do it. So let's have another list. Because it's made up of lists, let's form a list and bind it to, let's go. So let's have a list called L, and then it should be made up of names. It's assigned Leo G. And then age is 45. Does Leo has insurance? Yes. True. Let's run. And let's have the list. I hope we are following closely. Someone is behind me. I said, no, leave it behind, follow. Later, you sit down, you understand all this. So we want to add this list, which is made up of Leo, age 45, insurance, to our data frame. And so we come and say patients should be R bind. And then we have patients, add the list L to patients. Let's run. We have an error. I believe it's here, ages. Yeah. So let's run it again. Let's run it again. Let's run this again. Warning. Message in. Hold. I did run it and it ran. I'm wondering why it's not running here. So let me look at my R.
Okay, on my site, it actually ran.
Come again.
I actually managed to run it and add the third person, the third patient.
It ran for you.
Yes, yes.
Hey, what's happening to my code? Okay, so what am I doing wrong?
No,
Or
so
are you running it in
I have
R?
an
Or
error like you.
come
Could you
again?
please show the script?
I have the same message of you, Professor, so like a warning message.
Me too.
You also have the error.
Yes.
Yes, I have the same error message.
Okay.
It's
so
the same error, yes.
Yeah, the person whose code did run, what did you do for it to run?
I actually followed what you were actually saying. So
And
I'm
then it
trying to
ran.
actually yes, it actually ran. So I'm not sure where you actually got it wrong.
Hello?
But then I was actually following all your steps. Then I managed to actually run it.
The problem is on the name of the age. We have age with X and age without X somewhere.
Yeah,
In
so
the
I've corrected it. Names, ages, insurance. And then let me have this. And let me have this. So something is happening. So let's note down line 101. I'll fix it during the break. 101. Something is happening. Okay, so note down line 101. So that's just by the way. And we can also add.
Sir.
I'm trying to figure out what was the problem.
Sir.
Yeah.
Can you possibly use check the inverted commas for the age? Probably make it a double.
No. The inverted age is
the name, sorry.
No. Ages.
Because I realized in the error, no, the names, the Eugene.
So you have names.
Possibly it should be. So names is equal to
No.
inverted commas.
No. I explained to you that this sign is not equal to. It's assigned.
Not the equal to sign. Yes, I don't mean the equal to sign. I mean the inverted commas in which the age lies. In which the name lies, the name.
The name is a string. And no matter what, because it is a string, it has to be in single quotes.
Okay.
So I'll check on that. It ran for me before I made the notes. I don't know what really happened. So let's leave this slide and the next slide, and I'll come back to it. So here, let's look at data frames. Data, we are still on data frames. I'll come back to that error. When you install R, it comes with what we call libraries. And a library. So you are saying that this should be in uppercase, what do you call it, double quotes. I'm wondering. Double quotes, I'm wondering. Double quotes, this. And this. And this. No. That is not the solution. I'll come back to that after we've gone for a break. Now, when you install R comes with what you call libraries. And a library is made up of functions and data sets. I explained a function helps you do something by taking an input, then it's going to process the input to give you output. And so far, the functions we've been using, think about them. S apply, L apply, and all those functions, they are contained in libraries. Some libraries, they come with the installation. And so in those libraries, you find free functions like log and so on and so forth. Some other functions, we have to install them. And so let's say you are into medical research. Medical research, one function or one library that is used for medical research is called bioconductor. And so if you are going to be using that function, you have to install that function. I work a lot in time series. And so I have to install the library which does time series. And so for the free functions, let's just type library. Let's just type library. Type library. Library function. And run. When you run, you are going to see the functions that you have, which comes with the installation of your R. I have base, I have compiler, I have crayon, I have data sets, and so on and so forth. You are going to see some functions in my space that are not in your space because I've been using R for so long. And so one of the functions that come free for us is called data sets. For you to use any function, you've got to import the function into your R. And to import the function, all that you need to do is library and then the package. Suppose I am interested in the datasets package. Dataset package contains lots of datasets that you can use to learn R. I'll just do library data, library data sets. Then from there, you run. Once I do this, everything in data sets is made available to me. And so one of the data sets that you have in data sets is called Titanic. Let's look at it. Titanic. And Titanic should be data dot frame into bracket Titanic. Let's run. And so the Titanic data set is from a package called datasets. For me to use Titanic, I've got to import data sets. And I'm converting Titanic to a data frame, storing it in Titanic. And so once again, Titanic is being assigned data.frame into bracket Titanic. This is uppercase. And this is what is contained in data sets. I repeat again, this operator is not equal to. I said it's called what? Assigned. Let's look at the first few values of Titanic. So you type head, Titanic, head, Titanic. Let's run. This is the top 6 observations of Titanic. You have first class, you have male, age, the person is a child, survived, no. How many of them? 0. Second class, third class, they have crew, and so on and so forth. We'd like to see the tail end of our data. The tail end of our data. So let's do tail Titanic. Let's run. And it also gives us 6 values. You can increase or decrease the number of values that you want to see. And so I can do tail Titanic, and then let's say I want 10 values. So when you run, this is what you are going to get. 10 values. We'd like to know the names of the columns. And so you do names, and then Titanic, you do this, it gives you this. That is, it gives you class, sex, age, survived, and how many people survived. That is the names of the variables, as you can see here. Class, sex, age, survived, and frequency. Would like to take out some of the values. Would like to take out some of the values. So we do Titanic, then square brackets. We just want the first two values. First two values. And then we bring this. Take note of this. You see, it's a one of class. And so when teaching is going on and then you are up to some other thing, you are going to miss a lot. Here we are saying the first here is what takes the rows. And the next one is what takes the columns. And so we are saying, give me row 1 and 2. But in the columns, I haven't specified anything. It means give me all the columns. Again, when you write this, when you do this, Titanic, the first value here represents the rows, and the second value represents the columns. If you didn't bring a column, that means you are saying, give me all the columns. And so nothing there means all. And so here, we have row 1 and 2. But then in the column, it's empty. So give me everything. Let's see. So you have row 1 and then row 2. The columns, give me all the columns. That is how you can subset your data for analysis. So we come across it, that is head. Come across it, that is tail. Yeah. Now, sometimes when you collect your data will have strange values. Either the data is missing, or somebody miscaptured something, a lot. So you can see what is in your data by doing edit. And then let's give edit our data frame. I actually don't use R in the Jupyter environment. I'm having to use it because I want the class to be quick, to prevent you from making errors. What I use is plain vanilla R. And, you know, as an engineer, that works for me. So let's do edit Titanic and see. Ooh, I said it. Yep, 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 yep. So edit Titanic did not work in Jupyter. Let me show you how it works in R. So we have this, we have this, we have this. Okay. So can you see the R on your screen?
Yes,
Prof.
yes, it's visible.
Okay.
Yes.
So I do this and it's too small. Let me make it big, slightly big. Boom, boom, boom. 15, 20, 22. Yeah. So I do edit. You see, when you are typing in R and then you do opening bracket, it does not automatically close it for you. And that is why you are likely to be making errors. And when you make errors, trying to fix those errors will not move on. But I am used to it, that when you open something, you have to close. So Titanic, and when I do this, can you see on your screen?
Yes, Prof.
Yes.
Yes. So when you have data and then you want to correct something, you want to know whether your data has been captured properly. You do that and then you come and scroll through. You scroll through. Suppose male here on line 17. Suppose this place should have been female. You just click on it and then you do female. Then you do enter. Suppose here should be, we wrote sex. Suppose nowadays we want to write gender instead of sex or whatever it is. You just click and then it comes up. And so you can change it to gender. And then you press enter. It has changed. And so you use edit, your data frame, to edit your code. So all of us should take it on upon ourselves to find what Jupyter uses. What Jupyter uses in doing this particular thing. That's all. We like an age. So you want an age variable. You type Titanic. And then you do age. So here I'm saying, go into Titanic and give me all the ages. So for the row, I did not state anything in the row. If nothing has been stated in the row, it means give me all the rows of the column what? Ages. And so when I run, this is what I have. The levels. whether someone is a child, is an adult, a child is an adult, and so on and so forth. I want the number of people that survived. Look at it. Survived. I want survived. You saw what we did in the list. We said you can use the name or you can use the $sign. So I do Titanic, and then I bring the $sign, and then I say survived. When I do that, the list we see survive is problem again. Oh, no. That okay. So survived is uppercase S. Uppercase S. And I do it. It will give me the values. And so no, they didn't survive. Yes, they survived. That is the way you can assess your data frame and do all these sort of things before you start your data analysis. Okay. And so you can add a new variable to your data frame. We saw that with lists, you can add new variables. And let's look at our data frame again. Let's do head Titanic. Let's do head Titanic. Suppose we are interested in adding another column here. Adding another column. And that column, we want a proportion of people that survived. And so now you have class, sex, age, survived, frequency. We want to add another column that says survival proportion. And if you recall what we did in the lists, if you recall what we did in the list, to add something, we just take the data frame and then we do survived proportion. Proportion is assigned Titanic, assigned the frequency. Let's look at how this spell frequency. F, capital F, R, E, Q. And then divided by the summation, which is a free function given by R. And then we do Titanic dollar function frequency. We want the proportion, and proportion should be the frequency of one segment over the total frequency. Let's do enter. That is it. And then let's do head Titanic. We run. So you can see now survival proportion has been added to our existing variables. That is the code.
I mean, we haven't yet gone for a break.
Come again. Right. So it's 1 o'clock. We'll go out for break again. And those who can have coffee, let them have coffee. And I will do I'll give a half-hour break now so that all of us will go and have lunch. And so let's come back at 1:30. Let's come back at 1:30. Calvin. Okay. And so let's look at what we call program flow. Now, by default, the programs that we write flow sequentially. That is, line 1 is going to be executed before line 2, before line 3, 4, and so on and so forth. But sometimes program logic requires that the program takes paths. So the program will execute up to a point and then test a condition. If the condition is true, the program will execute a type of code. And then when it is false, it will execute a different sequence of what? Code. Or sometimes certain operations in our program logic need to be executed X number of times. So you have to do it until a certain condition becomes false. Once the condition becomes false, the program jumps out of that part and continue with the sequential or any other structure that it needs. And so this is an example. This is an example. Good. On your screen. So let's look at the program logic here. It starts with the question, do you have homework? Then if you say no, it detects that you might be lying. If you say yes, then it goes ahead. Is there something else you rather do? If you say no, it says get a life. If you say yes, it's okay. Is the program, is the homework due in less than 12 hours? If yes, then you have to start working. If no, you've got to, you have some time to watch television, check email, Facebook, have a snack, and then you come back to check the time again. So some places it goes sequentially, others it has branches, others it goes over and over and over again. That is basically how we program. You've got to follow the logic, and some logic will say, okay, from A, you go to B, you go to C. And then some will say from C, you have to branch to G. And some will say from G, you have to do something over and over and over again. So basically, computer code executes in 3 modes. That is sequentially, branch, and then it loops or iterate. Let's look at the conditional statements or the branch statements. The branch statements, we use the if statement to execute it. For example, if you are hungry, what do? You eat something. If the alarm clock rings, you get up. And so if is one example of what? A branch statement. Then you can also have what you call if else. You saw in the if statement, if you are hungry, eat something. What if you are not hungry? The program did not make provision for that. If the alarm clock rings, get up. What about if it doesn't ring? We did not make provision for that. And so all that we have is an if statement. We come to the if else. The if else is, in case the if is false, what will you do? So the example is this. If the traffic light is green, then walk. Else, stop. If the cup of coffee is empty, refill. Else, drink. So in the if else statement, we've made provision for both true and false. If it's true, we are going to execute the true block. If it's false, we are going to execute the false block. Then you can have multiple if statements. An example is this. If it's warm and dry outside, then wear a t-shirt. Or if it's warm and rainy, wear a t-shirt and a jacket. Else, if it's cold and dry, wear a sweater or a sweatshirt. Else, stay at home. This is the multiple if expression. Let's quickly do logic before we come to write the code. Logical expressions express something that can either be true or false. And when the condition evaluates to true, the if block is executed. If it evaluates to false, well, maybe provision has not been made for false, or provision has been made for false. And so logic expressions are what you use in doing the if or the else expressions. We have what is called logic and relational operators. We said addition, subtraction, multiplication, division. We call those things operators, mathematical operators. In addition to that, we have what is called relational operators. Something can be less or greater, less than or equal to, and not equal to. And then the logical operators, we have the not, the end is the ampersand. And then we have the or, and then end again for engineers, or for engineers, and then XOR for also engineers. What you might be interested in is not and or. So I'm going to have my Jupiter, and let's have not true. Let's have not true. Something that is not true, what do you think it will be?
An
False.
error?
False. So we execute and it says false. Something that is true or false, what will it be? Let's type true or false. What will it be?
I suggest true.
Why?
It's either of the true. It's either true
Exactly.
or it's false.
Exactly. So we do it. We get true, because a statement can be either true or false. What about true and false? True and false. What will it be? What will true and false be?
False.
It's false.
Yeah, because you can have a statement that is both true and false. So when you execute, you are going to get false. And let's say we have 55 greater than or equal to 15. When you execute this, the answer is obviously true. So these are logic expressions. A logic expression results in a Boolean. A logic expression results a logical expression results in a Boolean. Boolean. A Boolean is something that is either true or false. Yeah. So and then you can have what is called value matching in or not in character operations. Let's look at if statements. If statements. You have if. So to do the if statement, we bring in the keyword if, and then into bracket a condition, and then what has to be executed if the condition is true. So the condition here executes and evaluates to either true or false. if this condition turns out to be true, the code that we have in action would execute. But if it turns out to be false, nothing happens. Nothing happens. So if, and then you evaluate the condition. The condition is a logical expression. And a logical expression means it will either be true or false. Yeah. Okay. So let's execute this and see. Let's make X to be assigned 8. And let's do if. Let's have the brackets. X assigned 8. Then we press enter, not shift enter. Then let's have X less than 10. Let's jump out of it and have a pair of braces. A pair of braces. Then let's press enter. If you press enter, you are going to see that the cursor will be offset from your if. And then let's type in cat function. And then let's have single quotes. X is smaller than 10. And so look at the logic here. 8 has been assigned to X. And then in your if statement, you are testing whether X is less than 10. If that turns out to be true, then we execute this statement. If it turns out to be false, nothing happens. So let's execute. We do control execute. Then it says X is smaller than 10. X is smaller than 10. But suppose X was assigned the number 12. So you have if into bracket X less than 10. If that is true, the statement cat X is smaller than 10 will execute. But if it turns out to be false, nothing will happen because we did not make provision for the false situation. So let's execute. Nothing happened because this statement here turns out to be false. This therefore executes because it is the true block. No provision was made for the false block. Now, if else statements. You still have the if statement. You still have the if statement. And then it tests a condition here. If that condition happens to be true, action 1 is executed. But if the condition happens to be false, then action 2 is executed. And so let's do it again. X is assigned 8. We do if X is less than 10, we have a pair of braces. What should we do? We want to print something to see X is smaller than 10. Now let's come to the end of the brace. That is, jump out of the brace. And then put here else. And then bring another brace. You do this. So when X is less than 10, the true block, that is the first to the last brace, will execute. Else, that is when it is false, you print X is larger than 10. Let's execute. Because X is smaller than 10, is this block that executed. I'm going to make it 12. When you come here, X is less than 12. It will put, in place of X, it will put 12. 12 is less than 10. That is what? False. And so this block does not execute. It's this block that would execute. And so let me run. You can see X is larger than 10. And then you have the nested conditions. That one will be left with you to try. Yeah. And so we come to loops. Ooh. The slides available to you so that you will be going through it gradually before we meet again. And when you want to save your Jupyter, just go to File, Save As, and then put the name here. That is Computational Statistics 1. Computational Statistics 1. And then you click on Save. When you do that, you see here it says Computational Statistics 1. You can then close the browser. anytime you want to get back to it. So I'm going to close the browser. And I'll close this one too. Anytime you want to get back to it, we'll just come to our Windows, Start, and then Anaconda. Now you click on Jupyter. After some time, Jupyter will open. And then Jupyter, you scroll down, then you see your computational statistics 1. When you click on it, it will open. Yeah. And so this is what we've been doing today. Oh, come on. Yeah. This is what we've been doing today. It's all there for you. So, any questions? Any questions? Okay. I'll see you again on Tuesday. For now, I'm sending the slides to Kelvin, and then he will make sure you have the slides. Bye-bye.
Thank you, Professor Carl.
Thank you
Bye-bye.
for the lesson.
Bye.
Thanks.